All right, today we're going to crack open the internet's secret address book. I'm talking about IPv4, that invisible system that makes sure every email you send, every video you watch, actually gets where it's supposed to go. Let's dive right in and see how this thing really ticks. But have you ever really thought about it? I mean, how does your computer, sitting right there on your desk, manage to find a website that's hosted on a server thousands of miles away? It feels like magic, right? Well, it's not. It all comes down to one thing: a unique address, kind of like a digital fingerprint for every single device connected to the internet. So here's the game plan. We'll start with the internet's original postal system. Then we'll get into the whole public versus private address thing, a really clever trick that basically saved the internet. After that, we'll talk about slicing up networks to make them more efficient, do a quick hands-on example to make it all click, and then wrap up by showing you how all of this is happening right now in your own home. Okay, first up, the internet's postal system. Let's start with the absolute basics. Think about it like this. For the mailman to deliver a letter, your house needs a unique address, right? The internet works the exact same way. Every single device needs its own unique mailing address so that those little packets of data, the letters of the internet, can find their way to the right digital doorstep. So what does one of these addresses actually look like? Well, to a computer, an IPv4 address is just a long string of 32 ones and zeros. But for us humans, that's a nightmare to read. So we break it up into 4 numbers separated by dots. Each of those numbers can be anything from 0 to 255. And that simple format right there became the universal language for finding absolutely everything online, from massive Google data centers all the way down to the phone in your hand. All right, so back in the day, when the internet was just getting started, the folks who built it needed a way to organize all these new addresses. Their first idea was something called address classes. Basically, it was a way to sort the whole internet into different sized buckets. A simple idea for sure, but, well, as you're about to see, it was way too rigid. And when I say different sizes, I mean wildly different. A single Class A network had room for over 16 million addresses. That's like giving an entire country one single postal code. It's just massive. Then you had Class B, which was more like a city, and Class C, a little neighborhood. You can probably already see the problem here, can't you? It was just so wasteful. Huge chunks of addresses would go completely unused. And all that waste led directly to a massive problem: the address crisis. Seriously, the internet was exploding in popularity, and we were actually literally running out of addresses. This was a big deal. It forced the engineers to get really creative and come up with a super clever solution. See, a 32-bit number gives you about 4.3 billion possible addresses. Now, back in the 70s or 80s, that probably sounded like an infinite number. I mean, who could imagine more than 4 billion computers? But then came the PC revolution, and then smartphones, and servers, and smart toasters, and suddenly we slammed headfirst into a wall called IPv4 address exhaustion. There just weren't enough addresses to go around. So, what was the brilliant solution? They decided to split addresses into 2 different kinds: public and private. Here's the apartment building analogy again, because it's perfect. Your public IP is like the main street address of the entire apartment complex. It has to be totally unique in the whole world. But your private IPs? Those are just the apartment numbers: apartment 101, 102, 103. They can be reused in every single apartment building on the planet, as long as they're unique inside their own building. Or, in our case, inside your own local network. So they officially set aside a few special blocks of addresses just for this purpose, for these private networks. Anyone, anywhere can use them inside their home or their office. No permission needed. In fact, go ahead and check your computer's IP address right now. I'll bet you $1 it starts with 192.168 or maybe 10 dot something. That's a private IP. Now, there are a couple other oddball addresses you should know about. First is the loopback address. It's always 127.0.0.1. Think of it as your computer talking to itself. It's just a way to test if its own networking software is working correctly. Then you have something called API-PA. This is what happens when your computer gets lost. If it can't find the main server that hands out addresses, it basically just makes one up for itself. It's a temporary thing, just so it can talk to other lost devices on the same network. Okay, so private addresses were a huge help, right? But it only solved part of the problem. We still needed to be way smarter about how we used the precious few public addresses we had left. And that brings us to the next big idea: subnetting. So, if you have an IP address, how does your computer know which part is the neighborhood, the network, and which part is the specific house number, the device itself? That's where the subnet mask comes in. It's another 32-bit number, and its only job is to draw a line in the sand. It tells the computer, okay, this part of the address is the network, and that part is the host. Now, writing out a full subnet mask like 255.255.255.0, it gets old pretty fast. It's just clunky. So to make life easier, we came up with a shorthand called CIDR. That stands for Classless Interdomain Routing. All it is a slash followed by a number. That number just tells you how many bits are in the network part of the address. It's way cleaner, and it was a huge deal because it finally let us break free from those old, wasteful A, B, and C classes. It's super simple. For example, that common mask, 255, 255, 255, 0, means the first 24 bits are for the network. So in CIDR, we just write /24. Easy, right? And this flexibility is what lets us do something called variable length subnet masking, or VLSM. It just means we can now create networks of literally any size we need. Super efficient. All right, enough theory. Theory is great, but let's actually get our hands dirty and see how this works in the real world. We're going to take a single IP address and, using what we just learned, we're going to map out its entire network. So, here's our challenge. We're given one single address, 192.168.100.17, with a /29 mask. That's it. From just those two pieces of information, we can figure out everything else. We can find the network's ID, all the valid IP addresses we can actually use for devices, and something called the broadcast address. Ready? Let's do this. Step 1. That /29 tells us our mask is 255.255.255.248. Step 2. We need to find our magic number, the block size. Just take 256 and subtract that last number, 248. The answer is 8. That means our networks happen in jumps of 8. So let's count. 0, 8, 16, 24, and so on. Our address is .17, right? Well, where does that fall? It's in the .16 network. See? Simple. Now the broadcast address is always the number right before the next network starts, so that's .23. And finally, the valid addresses you can actually assign to your computers are everything in between the network and the broadcast. So from .17 all the way to .22. And just like that, with a little bit of subtraction, we've mapped the whole thing out. Okay, for our last section, let's bring this all home. Literally. We're going to connect all of these ideas directly to what's happening on your home network right now. Think about it. When your laptop wants to go to a website, it can't just connect directly to the internet. It needs to go through a single exit door for your whole network. It's like the central mailroom for an office building. That exit door has a name. The default gateway. And yep, you guessed it, for 99% of us, that's just our home Wi-Fi router. And this is where the magic really happens. Your router is the master of ceremonies. It hands out all those private IP addresses, the 192.168 ones, to your phone, your laptop, your smart TV. Then it uses a trick called network address translation, or NAT, to let all of those different devices share the one single public IP address that your internet provider gave you. It's a gatekeeper, a translator, and a traffic cop, all rolled into one. So that leaves us with one pretty huge question. All the stuff we talked about, private addresses, NAT, subnetting, they were all brilliant fixes that kept IPv4 from collapsing. But at the end of the day, they're just patches. The world is talking about 50 billion new internet-connected devices coming online soon. How on earth are we going to connect all of them with only 4.3 billion addresses? The answer is a completely new system called IPv6. But that, my friends, is a story for another time.